Hello everyone. Today let us discuss about some important terms in current electricity. Because if we know these important terms, it will be easy for us for the further derivations. Okay, let's start with our simple Ohm's law. So we have seen the Ohm's law. V is proportional to I. This is Ohm's law. V is proportional to I. And voltage and current are always proportional to each other. Next step after proportionality comes is equal with a constant. So V is equal to R into I, where R is called as the constant of proportionality and it is called as resistance. So resistance is most important throughout this chapter because we get lot of numericals related to resistance only. So first you should know the resistance. So resistance is an obstacle for the flow of current. So current is just like the water flow. So whenever a pipe is there, like a water pipe is there, and inside the pipe, if it is filled with mud and stones like this, the water cannot come out freely. So that is, these stones and mud, they work as the resistance for this flow of water. Similar to that, whenever we have a conductor, that is a conductor is there, conductor means a wire or something which is conducting the electricity, then current is flowing through that conductor. This is a conductor, for example, and current is flowing. Current means flow of electrons. They are flowing from one place to the other place. That's nothing but current. When current is flowing, sometimes there is a resistance for the flow of current. So that is denoted by capital R. So R is a constant of proportionality where it is called as the resistance. Now V is equal to IR. This is the most important formula that is called as the Ohm's law. Let's continue further. This resistance, 2 points are there. Resistance is directly proportional to length of the wire and resistance is inversely proportional to area, that is cross sectional area of the conductor. So if you take, for example, if you take water example only, so you have taken two pipes. One pipe is a long pipe and another pipe is a short pipe, and water will reach very fast from the short pipe, that is the second pipe, because length is small. That means current flows freely within with a small wire. That is R is proportional, that is resistance is proportional to L. That means current is flowing freely for a short wire because resistance is less for the short wire and resistance is more for the long wire. Similarly, if you take for water also, let us take water example. If we have a thick pipe like this and then another is a small pipe like this, means cross sectional area. So the first one has a big cross sectional area, second one has a small cross sectional area. Then through this one, the first one, the water flows freely because cross sectional area is more. Through the second pipe, the water flows not that much because its cross sectional area is less. So from this, what we can understand, resistance is more for a thin wire, resistance is less for a thick wire. So resistance mainly depends on two things. One is R, that is resistance is directly proportional to length, resistance is inversely proportional to cross sectional area. Combining them together, we can write R is proportional to L by A. Always I tell you, after proportionality symbol, then immediately the very next step is R is equal to some constant into L by A. Every time after proportionality we get is equal to and one constant. Here this is the constant, that is rho. This is called as rho. We pronounce it as rho, where rho is the resistivity. It's called as resistivity. We are learning another new term. So once again I repeat, R is proportional to L. R is inversely proportional to cross-sectional area. Combining them together, we write R is proportional to L by A. Then R is equal to rho L by A, where rho is called as constant of proportionality, that is called as resistivity. That is called as the resistivity. So this resistivity, it depends on the material of the conductor, but it does not depend upon the dimensions. This is one of the most important formulas of this chapter. R is equal to rho L by A. And most of the children think, because from this formula we can write like rho is equal to RA by L, means you have seen this formula, R is equal to rho L by A. Therefore, rho is equal to RA by L. Then the people think, the children think, rho is depending on area and L, but that is wrong. Rho does not depend upon dimensions. It purely depends on the material of the wire. Now coming to the point, previously we have seen Ohm's law just now, that is equation 1. This is equation 1, V is equal to R into I. Now we have seen R is equal to rho L by A. So Ohm's law is V is equal to IR. Now we have seen this formula, R is equal to rho L by A. This is equation 1, this is equation 2. Substituting 2 in 1, then V is equal to I. R means rho L by A. So we can also write it as rho into L, I by A separately. I am putting in a bracket. Another new term we are learning, I by A. I by A means it is called as current density, denoted by a letter small j, where J is called as current density, that is current per unit area. Current per unit area. So we have taken equation 1, Ohm's law, and substituted the value of R, that is rho L by A, but I by A is a current density. So let us see, and then further we will proceed. So current density is a vector, whereas current is a scalar. Current has both magnitude and direction, but current is a scalar, but current density is a vector. Why? Because J is equal to I by A. I is a scalar, but area is a vector. Therefore, scalar divided by vector, J becomes a vector. So current density is a vector. Now let's further continue. And we know, if the conductor is like this, and we have given it a potential difference of V across its ends, and electric field is E, which is developed, that is uniform electric field in the conductor, and the length of the conductor is L. So what we are learning now is, we have seen in the previous chapter, second chapter, relationship between V and E, that is potential and electric field. Potential and electric field. If E is the uniform electric field, V is the potential difference across the ends of the conductor, and L is the conductor's length, then V is equal to E into L. Let it be equation number 4. Because we have seen in the second chapter, relationship between potential electric field and length. V is equal to E into L. So this is our conductor. As I have told you, we have applied a potential of V. E is the electric field, L is the length. Then relationship between them, V is equal to E into L. This is equation number 4. And previously we have seen V formula. Just now I have shown you equation number 3 here. This is also V. V is equal to rho L I by A. V is equal to rho L I by A. Now V is equal to E into L. This is equation 3, this is equation 4. Both are V only. Both formulas are related to potential difference. LHS is same for both of them. So let us equate both of them. Let us equate both of them and further proceed. Let us equate both of them, equation 3 and 4. Then we get this EL is equal to rho L I by A. Just now I told you I by A is J, that is current density. Then EL is equal to rho L into J. And both the sides L and L cancel. Now you will get E is equal to rho into J, or E is equal to J into rho. So this is the relationship between current density, electric field and resistivity. Further, it is electric field is a vector and current density is a vector, just now I told you, and we can write in the vectorial form E bar is equal to rho into J bar, equation number 5. That is equation number 5. E bar is equal to, that is vectorial form, E bar is equal to J bar into rho. So that is the vectorial form of this relationship. Let's continue further. And another new term I am teaching, reciprocal of resistivity is called as conductivity. That is given by the letter sigma. That is sigma is equal to 1 by rho. Sigma is equal to 1 by rho. So once again, reciprocal of resistivity is called as conductivity. Conductivity is denoted by the letter sigma. It is not the same sigma which we have used in the first chapter. In the first chapter, sigma is used for surface charge density, that is charge per unit area. But we are not using that relationship now. This is a different relationship. Sigma is equal to 1 by rho. Sigma is not surface charge density here. It is nothing but conductivity. It is called as conductivity. Sigma is equal to 1 by rho. Therefore, if you take this relationship again, E is equal to J into rho. Let us further continue. E is equal to J into rho. And therefore, J is equal to E by rho. That is E into 1 by rho. But 1 by rho is equal to sigma. Therefore, J is equal to E into sigma. This is another relationship, that is current density we have expressed in terms of conductivity and electric field. And we have to write in vectorial form J bar is equal to sigma into E bar. So vectorial form we can write, because J is a vector. Electric field is also a vector. So we can write the relationship between them. J bar is equal to sigma into E bar. This is the relationship between current density, conductivity, electric field. So what all we have learnt today is, we learnt Ohm's law, which is V is equal to IR, and we learnt the terms resistance and resistivity and current density, conductivity, and the relationships between various quantities. So this is all about very different terms which we have learned. In my next video, I will tell some more terms like related to the third chapter, relaxation time tau, and then drift velocity Vd, and then I will also tell about mobility, and then we will derive the expressions, many expressions, that is the relationships between resistivity, relaxation time, and then electron density, and so many terms we will learn in the coming video. So first you learn these terms, and further we can proceed with another derivation in our next video, and we will explain more derivations in the coming days. Thank you for watching this video. Until we meet in the next video, bye. God bless you all.